Okay, welcome everyone again to this Warsaw University Astronomical Observatory Tuesday seminar series. Today we have our lecture room full, packed with people. I'm very glad to see that, but welcome also to people who are on Zoom and or YouTube. Today our special guest from London, Giovanna Tinetti, who is from University College London, and she is the PI of a forthcoming mission called Ariel, who is going to develop and study planets, and Giovanna is going to tell us about this. And Giovanna has been a guest of us of this day, looking for explaining the whole mission to us, and we are very much looking forward to the seminar here and to all the collaborations which are going to arise from this. So Giovanna, the floor is yours, please.
Thank you so much. Okay, good afternoon to everybody. It's a great honor and a great pleasure for me to be here today. I would really like to thank you all for having invited me. Absolutely delighted.
Click on anywhere. That should work.
Okay, let's go with the low tech. Okay, in the past couple of decades, we have learned that planets are really ubiquitous, and we are expecting to have at least as many planets as stars in our galaxy. And of course, we would extend this information also to our galaxies. So this is great. It means that we're expecting billions and billions of planets, even in the Milky Way alone, which is fantastic. It's a great advantage if you're comparing this with our colleagues, cosmologists, that they have just one universe. You can see what kind of advantage we have having to take care of all these planets. But unfortunately, we don't know yet all these billions of planets that statistically speaking are expected. The number of confirmed planets around our stars is now around 5,000, which is such an impressive number. And the fact that most of them seems to be organized in planetary system is very interesting information, and we already start to have more candidates. But I think, in my view, the most revolutionary message that we are seeing out of the evidence coming out of discoveries of exosolar planets is the fact that the solar system doesn't seem to be the paradigm of planetary system in our universe, well, at least in our Milky Way. And I think this is an incredible message. It's almost a second Copernican revolution. And I'm aware that I'm saying this in a room where I can just see the portraits of Copernicus. Okay, no offense, but it looks like your message is even stronger, because it looks like it's not just the sun that is not the center of the universe. The Earth that is at the center of the universe. It's also that the solar system doesn't seem to be the paradigm of planetary system. And of course, we want to understand why we're seeing all these diversities, planets discovered around our stars. So what you have here are two plots showing all these colorful dots are some of the planets being discovered with many different techniques so far, plotted against the same major axis and the planetary radius. And in this case, we're looking at the orbital eccentricity. And in the x-axis, the semi-major axis again. And so I think you don't have to analyze this plot so much to see that the solar system planet are just some example of this parameter space that seems to be covered by exosolar planets. And again, the diversity is really huge. And I'm not suggesting with this that the solar system planets are unique or very rare. Actually, we don't really know that, in part because we still have some biases in some of the techniques that we're using today to discover planets. But it is a fact that the solar system doesn't seem to be so representative. I think Kepler, the NASA Kepler mission, has helped quite a lot in understanding the galactic statistics. but also microlensing. And clearly here with the Ogle survey, there has been a huge contribution to this understanding of the galactic statistics. But what we're seeing, for instance, out of the Kepler measurements is that small planets seems to be much more common compared to large planets. And this was not necessarily an information that we were expecting. And most recent observations that are combining Kepler measurements, but also some Gaia measurements and also some measurements of stars from the ground are suggesting that not only small planets are more numerous out there, statistically speaking, but also this seems to come with this sort of bimodal distribution, something that at the moment is called radius value or radius gap. Clearly the question is, what are these objects that seems to come with this sort of bimodal distribution? And at first analysis, one could be tempted to say, okay, the objects that are clustering around the Earth radius must be rocky, and so they must be more similar to rocky type of planets like the Earth. And the second peak, presumably we're looking at volatile-rich exoplanets, either sub-Neptune or ocean worlds, so something like that. But of course, we still know very little about the planets in these two distributions. And so I think we need to be a little bit careful in not overinterpreting what we know, or certainly what we don't know. And what do we know exactly? Well, for planets that are discovered through transit, you have the radius of the planet, and if on top of that you have some measurements out of radial velocity or in principle astrometry, then you can get the mass of the planet. And then typically you know the distance between the star and the planet, and out of that you can, as zero order, estimate the planetary temperature. But of course these are relatively basic parameters, and out of that, in the community we already see many plots like this one that are plotting the current planets that have been discovered through transit and radial velocity. And we're looking at radii versus masses, and so effectively you're looking at the density of bulk density of these planets, and then you can see some plots with some models of the interior that are suggestive of the composition of these planets based on the bulk density. And this is fantastic, of course, but first of all, in particular, if you stay in the region where you're probably more smaller planets, you see that many models are actually interpreting well the observations, and so there is quite a lot of degeneracy. And as you can imagine, this is not completely unexpected. It's like if we're trying to describe human beings just looking at the density. We have a density that is a little bit higher than salty water, but hopefully we are more than that. And I think that to a degree the same is for planets. It's fantastic to have this first sort of characterization, but clearly we want to know much more. We're expecting that many of this diversity that we're seeing out there must be connecting to process of planet formation. And clearly, although there is a lot of work being done in modeling planet formation, we literally just starting to have true constraints out of observations. And many constraints are coming from ALMA measurements or direct imaging instruments in the near infrared. And these fantastic images of structural disks, which are the environments where planets are forming, are clearly very useful to start to constrain some of these models of planet formation. Not just the structure, but it's also the complexity of the chemistry of these superstellar disks is something that people were not expecting early on. That, and in addition, also the information that we we keep collecting out of solar system probe that are using isotopic ratios from meteorites or from in situ measurements. And these isotopic ratios are very helpful to start to see a history of the solar system. And this history of the solar system combined with what we're seeing out of ALMA, for instance, is quite strongly indicating that you need to form giant planets really early on and very fast in less than 1 million years, which is not something that traditional models were expecting. So all of a sudden you need to start rethinking about many of these models. So this is just an example to show how observational constraints are really extremely helpful to start to understand what's going on. And clearly later on, SKIA in the future might be quite useful to look at, if you're looking at ALMA observations, ALMA is sensitive to objects up to the millimeter size. But when you look at planet formation, you would like to see also objects which are slightly bigger. And certainly centimeter size objects are quite helpful to understand, for instance, the role of pebbles in planet formation. And SKIA might be able to tell us something about these centimeter size objects. So this is again to say that there are many observational constraints that we can hope for this particular area of research. But more in general, I think in the next decades, we have a long list of new questions that we want to start to address. And I mentioned before, to me, the biggest question is why the solar system is as it is, in particular compared to the diversity that we see out there. In general, I think it's important to start to understand the composition of exosolar planets. Well, perhaps this question about the weather is a little bit UK-centered. We are a bit obsessed about weather. But more in general, why they're so diverse, how do they form, and of course the question of visibility is something that we all have in mind. Now, a powerful diagnostic that combined to many other parameters can really help us understanding some of this complexity is the atmospheric composition. And so looking at the chemistry of these atmospheres. Why we're interested in that? Well, the atmosphere is the gaseous part of a planet. So in principle, and I will come back to that, you're able to do direct measurements of the gases that are present in the atmosphere and also the structure of these atmospheres. And the chemistry of an atmosphere is the result of many complex chemical and physical processes. And in this diagram, you can see some of these processes being highlighted. Now, of course, for one single object, it's very hard to disentangle the causes of the chemistry, because also here, of course, you have many degeneracies. But the hope that you have with exosolar planets compared to solar system planets is the number of these objects. So we have the unique opportunity with exoplanets to go for this statistical sort of analysis. And perhaps is by looking at a large number of objects that we can try to and think of disentangling many of these processes and understand their why they're as they are exoplanet atmospheres. Now, luckily for us, we already have a number of techniques to probe the atmosphere of exoplanets, and all of them are challenging because we should appreciate the fact that we're trying to extract signal that are typically 10 or a few tens of parts per million the flux of the stars, so they are challenging. But I think they're already delivering all of these techniques very intriguing and interesting results, and they're all very complementary. So it's not that one is better than the other. They all operate on different type of objects, and so in principle, one should really try to use all of them in synergy as much as we can. And so in particular, we have the so-called transit technique or combined light technique, where we are relying on a planet that is orbiting in an orbit for which at a certain point the planet is passing in front of the star and the observer, or going behind it during the eclipse. And if we know the relative position of the planet with respect to the star, then we can use this information to disentangle the contribution of the star from the contribution of the planet. Whereas for direct imaging, you're trying really to null out the contribution of the star compared to the planet, to really mask the star and really focus on the light that is coming from the planet. And also from the ground, more and more there are very successful observation done at very high resolution, more similar in a certain sense to the radial velocity technique. And again, also ground and high resolution observations are typically quite complementary to the observation you can do from space, that on the contrary are relatively low resolution, but over normally a broader Gaussian range. So I have just a few examples just to show you where we are with all these techniques and to give you some evidence of what's going on. So this is a beautiful spectrum that was taken with the GPI. Is a direct image planet, and so typically with this technique we're looking at planets that are located at a large separation from the star, and also they are typically giant planets and also quite young. And so this is very different type of population from the one you're probing through transit, whereas giant planets are typically orbiting close to the star, otherwise you wouldn't be able to do the transit technique in the first place. And it means that the transiting one have migrated in, and it's not necessarily the case of the direct image one. And so all of a sudden you're probing two different classes of planets. And so I think it's very important to compare those. One example from the ground, clearly from the ground, being able to go for a very high resolution, you are able to look at atomic or ionic species because you can identify single lines. And this is definitely something you cannot do from space, so extremely valuable. But at the same time, you're sometimes limited to a very narrow wavelength range, and it's harder then to understand what's going on in the continuum around that line. Now, so far, I think space telescope like Hubble and Spitzer have been very valuable to help understanding the composition, in particular of many gaseous planets, and typically these are all transiting exoplanets. And so I would say, pushing all together, the observation that we've done so far, we are counting about 80 gaseous planets that have been probed with one telescope or the other, not in a complete way. Most of the time, these data are quite sparse. Maybe you have the data of one of the instruments, but not our instruments. And even when you have multiple instruments that were used to record the data, as you can see here, when you combine data from Spitzer and different instrument on Hubble, you always have the danger that you're injecting some biases, because all these instruments are not necessarily calibrated one with each other at the level of 10 or a few tens of parts per million. So of course, that's the only thing we can do so far, so we're doing it, but we should be aware that we are injecting potentially some biases. And out of these studies, I would say water vapor has been the molecule that has been detected the most, in part because the WSC3 camera is probing between 1.1 and 1.7, and so is very sensitive to this particular molecule. But also other even more exotic molecules like some of these TIO or VO seems to be present in particular in many of these very hot objects. But it's fair to say that you know, we don't necessarily have a complete picture. Now, in a few cases, the observations were following the planet throughout the orbit, so not just looking at the planet while it's passing in front of the star or going behind it. And when that is happening, then is very useful what we're seeing, because we have the chance of monitor spectra of the planet at different phases. And as you can see here, these are observations that we're taking with Hubble WSC3. The spectrum is changing a lot throughout the orbit. Not necessarily for a change in the chemistry. Maybe there are changes in the chemistry. We're expecting changes of the chemistry, but we're not sensitive enough with current observation to see those now. But certainly we are sensitive enough to see changes in the thermal profile, so the vertical thermal profile, how the temperature of the atmosphere is changing as a function of pressure. You can probe this kind of profile out of this phase curve spectra. And so it's already very useful to start seeing how this thermal profile is changing as a function of phases. But we don't have so many observations for many planets, and so clearly it would be great to have more in the future. Also, I think that since now the number of exoplanets, atmospheres probed with Spitzer and Hubble starts to be a certain number, you start to see population studies, so not just individual planets being analyzed, but really a few tens of planets being analyzed and comparison being made among the observations and interpretation. So one of the latest one is this population study that we basically published, it came out yesterday, and this study that is led by Captain Shanja is including 25 gaseous planets measured in eclipse, combining Hubble and Spitzer, and with all the new caveats that comes from all these uncertainties that I mentioned so far, we start to see some trends. And so in some cases, there were some collective behaviors that are suggestive of some interesting physical and chemical properties of this atmosphere. So this particular plot that I'm showing here seems to suggest that for planets for which we're seeing a thermal inversion, so basically we see a stratosphere where the temperature is increasing with altitude, seems to be somehow correlated with the potential presence of some of these optical absorber like TiO, VO, TiH, and so on, that are very efficient absorber of light, and so could potentially justify this this inversion. This is just one of the trends that we are suggesting being present, but I'm very careful in my wording because I am fully aware that these data are still limited, but I just think it's very interesting to start to see some of these trends. And certainly with Hubble, the very first observations of smaller planets, so not necessarily gaseous one, but planets more in the regime of super-Earth or sub-Neptunes, are starting to come out, and just have a few examples here. Of course, these are very challenging observations for current observatories. But for instance, this is an atmosphere that was probed for around 55 Cancri. 55 Cancri is 8 masses planet and is orbiting around the star in less than 1 day. So the temperature at the surface is expected to be over 2000 Kelvin. So it's probably molten if there is a surface. And we're seeing this modulation that is suggestive of the presence of an atmosphere around this planet. What is the exact composition? We don't know, but even the fact that there might be an atmosphere, it's an information, because we don't know exactly what to expect out of those very extreme type of planets. And of course, the TRAPPIST-1 planets, these 7 small planets with the sizes between the size of the Earth and the size of Mars around an ultra-cool dwarf that were discovered by your collaborators some years ago, are extremely interesting targets, in particular for habitability. But for the moment, the spectra that you see here that were published by the Vita collaborators using Hubble, unfortunately, the error bars are too large to really try to understand what's going on. These planets are too cold, too small for current observatories, but definitely will be a great regime for James Webb. And a couple of other examples, K218b, it's a temperate planet, so 300 Kelvin or so type of temperature. We don't know exactly what is the nature of this planet. Is coming in the sort of second peak in the sort of volatile rich. Could be a sub-Neptune, could be an ancient world. It doesn't help that the star, the stellar radius and the stellar mass are not known with great level of certainty, and so all this uncertainty is sort of transferred to the uncertainty on the planet. But from an atmospheric perspective, I think it's quite uncontroversial that water vapor is present. and there must still be some hydrogen in the atmosphere, because otherwise we wouldn't be able to see the signal. And so that makes it a very, very interesting planet. And finally, I have this example of another super Earth. But I brought this example because in this particular case, the M dwarf, which is the Orion star, seems to be quite active. And despite the many models, I don't think we can conclude whether what we're seeing is a signal that's coming out of the atmosphere or is coming out of the stellar activity. So again, it's just a bit of a caveat that in particular for planets around active star, you need to do more measurements and to make sure that you're not looking at a signal that is a stellar one. Because of this, I think at UCL, since a few years, we have invested quite a lot in techniques to extract and analyze the data for exoplanet atmospheres. And in particular, we invested quite a lot in the use of machine learning to analyze some of this data. And many of these techniques seem to be quite helpful, in particular for current instrumentations. Of course, whether or not some of this technique can be used for future one, we shall see. I mean, every instrument has its own peculiarities, and not all techniques are valid for all the instruments. But I think it's very promising, and clearly this is something that we need to look even further to get rid of instrument systematic, but also stellar activity. And we also invested quite a lot in what we call in jargon spectral retrieval models. So given a spectrum, in particular when you have these relatively noisy spectra and a bit patchy because you have data not uniformly distributed across wavelengths, the way you interpret them, it is also very challenging, and you need to resist the temptation that not to include your priors in interpreting them. And so the best way that people have I've tried to address this issue is to use spectral retrieval models. So basically inverse models where you're trying to probe the parameter space of the atmospheric parameters, but also other more basic parameters using some Bayesian techniques, or even more recently some deep learning AI techniques, and so on and so forth. And so the entire idea here is you have a spectrum, and then you use this technique to not just to understand which molecule could cause some of the signatures, but also to quantify and assess the reliability of your interpretation, and whether you should be very careful, or you can be perhaps a little bit more optimistic in what you're seeing. And so what you take out of these models are these sort of posterior distributions, where you're trying to look at the correlation among parameters and try to understand how far you can believe what you're seeing, and how much, on the contrary, you need to be careful. All our models are all open source, so you can download everything, use all these models, and if you have any questions, just be in contact with us. Okay, so of course the current data are limited, but if you're interested in exoplanet atmospheres, this is the focus of my seminar. I think that the future will be very bright. James Webb has been successfully launched in December of the past year, and so we're all very curious to see finally spectra taken with an observatory that is very sensitive, and so in particular for planets like the TRAPPIST-1, the K218b, having a 6.5 meter telescope and extremely sensitive infrared detectors is really what you need, because these are the stars are very faint to start with, and you're looking at very small and cold planets, so you really need all the photons that you can. And so to me, James Webb will be absolutely fabulous. But focusing on the atmosphere, I mean, the rest of my talk will be about Ariel, which will be the first dedicated mission really to look at exoplanet atmosphere later on in 2029. But I will spend, before getting into Ariel, just a couple of words to say that with some other colleagues at UCL some years ago, we have opened a company that is called Blue Sky Space, because we wanted to see whether in parallel to all these great missions and observatories that are being built by government agencies like ESA, NASA, JAXA, and so on and so forth, whether there is some value in looking at some commercial opportunity. Of course, not to do missions like James Webb and Ariel, these were too expensive and too challenging, but small satellites that could be used in parallel, maybe to answer some of the easiest questions in this field. So the company is exactly what it's trying to do, creating new opportunities. And Twinkle is our first satellite we're looking into, is a small satellite in polar orbit that will be built by Airbus and ABB. And we're also looking at other potential satellites in the future, looking at our science cases. So I promised a few words about Ariel. And what is Ariel? Well, in 2015, we are proposed to the European Space Agency the idea to launch a space mission completely dedicated to the analysis and understanding of exoplanet atmospheres. And Ariel was selected in 2018 and then adopted in November 2020 to be the M4 mission for ESA to be launched in 2029. And Ariel will be launching L2 together with Comet Interceptor. We are talking about a 1 meter class telescope, so a small one compared to James Webb, but such a big one compared to the small satellite I was referring to before. And unique selling point of Ariel is to be able to cover simultaneously between 0.5 micron in the optical down to 7.8 micron in the infrared. And this is quite an advantage because by covering such a broad wave range, you don't have all the issues that we're seeing with current telescope, where we're trying to patch multiple observations from multiple facilities. And we can also be very efficient in looking at many planets because of this simultaneous coverage. I mean, even James Webb, which is fantastic, but if you want to cover a relatively broad wavelength range, you might need to repeat the observation with different instruments. And the fact that here you can do it in one shot, the entire wavelength, it's certainly a help in terms of efficiency. So what we want to probe is about 1,000 exoplanet atmospheres in 4 years of lifetime. We want to include both rocky and gaseous exoplanets around different types of stars, planets with different temperature. So we really want to make sure that we're having a large statistics of planets in the galaxy, out of which we can really extract the information that is needed to understand a bit more how planets are forming and evolving in the galaxy. So the spectral range was selected because it's quite optimal to both probe the presence of molecules in this atmosphere, but also the thermal profile, also the presence of clouds, and also how to mitigate the impact of stellar activity that can be monitored in the optical. Now, this picture was taken in Warsaw some years ago before the pandemic. It's in front of CBK. CBK is an important partner of the payload consortium of Ariel. That at the moment is including about 500 scientists and engineers from 16 ESA countries, and we have a contribution from NASA and JAXA. The spacecraft will be built by Airbus, but the payload will come again from this consortium, and it will be integrated at RAL in the UK in this big chamber here. I mentioned the role of CBK being quite central, and in particular, CBK will be responsible for building the FGS, which is responsible both for the pointing, so absolutely crucial, but on top of that, it's also containing an optical module that is containing a number of photometric bands in the optical and also spectrograph in the near infrared. We have the consortium science is being dealt by working groups. We have a large number of working groups with coordinators looking at different aspects of the science of Ariel, making sure that the chemistry, the analysis, the stellar activity, and so on and so forth are all taken care of. And so the science stays fresh, and there is a team of scientists that are monitoring the preparation of Ariel, and later on, when the data are available, will be in charge of interpreting this data. And the consortium is very open. If you're interested in joining the Ariel consortium, you can apply to the Ariel consortium membership. Here you have the link. You just have access to this website. And if you're working in an institute that is part of the consortium, is as easy as signing up, saying your expertise, your interest, and then you will be put in contact with all these working groups, and you can start helping us. So I hope many in this room and online will take the hint. We are thinking to have a sort of 4-tier approach. What is that? We want to optimize the breadth and the depth of the observations. And so on one end, we will start with a relatively, let's call it shallow survey. So a survey of 1,000 exoplanets, not necessarily doing very detailed observation at very high resolution. But then out of that, we want to select half of the planets and really go for a full characterization. And for a more limited number of objects, we want to follow them throughout the orbits, through phase curves, but or keep monitoring them through time to look at the temporal and spatial variability. Of course, the exercise of target selection has already started. Although, of course, this is an evolving exercise, and it will be frozen only just before the launch, and even after launch, we'll still have the possibility to make some changes. But in our simulations, using known data, known planet, and in particular, some of the target candidates that are coming out of TESS. TESS is certainly very helpful to look at and detect planets around very bright stars. We already have a long list of planets to select from. And so it's not just the number of planets that is useful, but is reassuring that the parameter space covered by these planets and stars is already quite diverse. So here you're seeing some of this parameter space as a function of planetary size and planetary temperature. We are doing similar exercises, looking at the completeness also of number of planets around different types of stars. And in this particular plot, in particular, you see the differences between where we were, even just a couple of years ago, before some of the TESS discoveries, where in particular, we were clearly missing many targets around M dwarfs. And now the parameter space around M dwarfs is much more complete. So it's not just the number that is changing, but it's also the ability to cover this parameter space that luckily is becoming better and better. And certainly we want to focus also on planetary systems. And again, very reassuring that TESS is identifying many of transiting planetary systems, not just individual planets. And we certainly want to include those because we're interested in comparative planetology. So I don't have time to go through all the science cases, but I just have a few examples. So we're doing, as you can imagine, many simulations. Many of the working groups are very proactive in looking at assessing, in particular, whether if there are some chemical trends, are we able to see them in the data of Ariel? And so this is one of these tests where it was injected a trend where the amount of water vapor in the atmosphere is a function of the temperature. And this is what you're retrieving out of the data. You can still see the trend. So again, reassuring. It means that if we have similar trends, we will be able to see it out of Ariel. We are also very interested about small planets, understanding the composition of the atmospheres, and that should help us understanding whether many of the small planets are sort of Neptunes, whether they're ocean planets, whether they are terrestrial planets like the Earth, or more exotic example like these carbon planets that have been suggested. suggested to be present. We don't know whether they are or not. Clearly, all these planets should have an atmosphere with a composition that is reflecting the interior. And so that's what we hope to see. And so clearly, the atmospheric composition will be very helpful. Finally, there is certainly a lot of interest among people working on planet formation to see whether it is true that there is a correlation between the elemental ratios in some of these atmospheres, in particular the giant one, and the metallicity of the star, or somehow if there is a correlation between the elemental ratios in the atmospheres and the potential provenance of planets, so the region in the disks where they might have formed. There's a lot of literature suggesting that, but if that is true or not, we need to understand from observations. Clearly we will need certainly all the help from the consortium, but also from the general community in selecting the final list of targets. We will have a website that will include updated information about all the potential targets, and anybody in the community will be able to see the potential performance of Ariel and even vote if they want to see the planets being included or not. Of course, as part of the website, it will be possible also to do some simulations of the atmosphere. And so we want to make sure with all these tools that we will be very receptive to all the inputs coming from the consortium for sure, from all these working groups, but also from the general community. We don't want to work in isolation. And because of that, we'll be extremely open in terms of data release. Many of the data will just be publicly available immediately without proprietary period. And it's just for some of the tiers that the consortium will have a 6 month proprietary period, and for a more limited number of planets 1 year. And this is because there are more challenging observations, and so we will need a bit more time to process all that. We're also engaging with the community of machine learning quite effectively through the challenges that are now coming out every year. The first two were done in collaboration with the European Conference on Machine Learning and have been a really, really big success. In particular, the winner of the 2001 is a small company in Portugal, and the winner has become quite famous because it was one of the national quiz in TV, and so it has become all of a sudden, you can see the video here, you can hear the questions about who is the winner this year of the challenge. So clearly we are, although I was not expecting, we are becoming part of the pop culture, which is fantastic. It's exactly where you want to be. There is another one for 2022, so watch out if you have any interest in participating. And perhaps something that many of you might be interested in contributing, in addition to the working groups I was mentioning before, is this citizen science initiative called Exo-Clock, where Exo-Clock team is working with amateur astronomers and professional one. And the idea is to use any telescope available anywhere in the world to monitor the ephemerides of Ariel. And this has been extremely successful. There were many papers already published in prestigious journals like APJS and so on and so forth. And so you can see the numbers is going really up. And so please join if you have any interest, because we certainly need much more help for the future. So I'm conscious of time, and so I might skip these 2 questions. And if you have any questions about JWST and ELTs, I'm more than happy to answer. And let me wrap up the conclusions. Exoplanets appear to be ubiquitous in our galaxy, and while the number of discovered exoplanets is increasing exponentially, for the moment we still know very little about that. But hopefully next decade things will change. We will have, in terms of parameter space being probed and new exoplanet being discovered, even more data coming out of space satellites like TESS, CUBES, and Plato, but also many other observations from the ground, not just through transit, but all the other techniques which are extremely important to fill this parameter space in a homogeneous way. But also when it comes to atmosphere, which was the focus of my seminar today, We are very lucky. We will have James Webb, Twinkle, many of our satellites, many of our observatories from the ground. And I'm personally looking forward to Ariel, because being a dedicated mission just to do this kind of work on Exo-atmosphere, I think will be a fantastic opportunity for everybody to get the big picture in terms of chemical surveys of exoplanets. And with that, I would like to thank you very much, and I'm happy to.
Thank you, Giovanna, for a great talk. Questions, please, here from the audience first. Elena.
So what would be the observing strategy? Is it already decided that, well, you will observe like several transits of this thousand of exoplanets, or like, is it already decided, the strategy?
Well, of course, there are already many plans, and I think it's important that we all think about how to do things, although the final plans, again, it will be put in place, will be confirmed only before launch. But let's say that we go with this 4-tier strategy that so far seems to be a good way to keep the breadth and the depth. The idea is for the tier 1, you typically need just a few events between 1, maximum 5 of transit and eclipse. And then you will need then to select for how many and which of the planets you go on with tier 2. And so at the moment in the plan, we have that roughly half of the planets looked at in tier 1 would be looked at in tier 2, meaning you're increasing the number of transit and eclipses so that you can get higher signal to noise and resolution data, out of which you can get more observations. For the tier 3 and 4, to a degree, you can select them before, because at the end of the day, there needs to be, in the case of tier 3, the idea is to have planets for which in one event you get spectacular signal to noise and resolution. We want to use these planets as benchmark, or to look at the variability through time and repeating observation. So again, we already have a list of those, and similarly for the phase curves. It doesn't mean that this plan will not change, because, for instance, we already know that one possibility is to give priorities to smaller planets if we think by 2029 that the giants will already sort it out. I think it's unlikely, but if it is the case, then maybe we can focus a little bit more on more challenging planets, and so maybe spend more time in a smaller number of individual planets rather than dedicating more time to the survey. I think we should also bear in mind that if the mission is working well, this 2 years extension will probably be granted. And so in a certain sense, we need to keep in mind in the back of our head that maybe some questions could come also in extended mission. So yeah.
Any more questions from here? No.
How you will be doing the photometry and spectroscopy? Will it be done somewhat simultaneously by some beam splitter or something like this, or separately?
Yes, there are some dichroics to split the light, yes, there are 4 dichroics, and so the light is being split in the various channels, and in particular there are 2 instruments on Ariel. One is the FGS that I was mentioning before, where you have 3 photometric bands in the visible, and then you have a spectrograph in the near infrared. And then you have a spectrograph in the mid-infrared covering between 2 micron and 7.8, and you have 2 separate spectrographs in that. So that's why we have these different dichroics.
Using some coronagraph for
no, luckily we don't need a coronagraph. I'm saying luckily because I know that a mission like Ariel is already challenging as it is. So luckily for engineers, they don't need to worry about coronagraph and a telescope that is highly polished. By using the transit technique, you will effectively be using the position of the planet with respect to the star to separate the atmosphere of the planet from the contribution of the star. If we were doing direct imaging, which is, for instance, the technique that will be used by the Nancy Roman, then you will need a coronagraph. Once you have a coronagraph, you also need a bigger telescope because in order to make sure that you have enough contrast and enough angular resolution, then that asks for a bigger dish. But in transit, you don't need all that, and so you just collecting all the photons. And a 1 meter class is enough if you're looking at planets around very bright stars.
And I guess because you split light into many things, you're probably magnitude limited. What is the rough magnitude limit in kind of in optical bands in VBAD, let's say?
So I think, I think we have a sweet spot. I mean, of course, you can push even to fainter target, but it's not in the interest of the mission pushing for very faint targets, because it means that then you need to pile up multiple transits. So it's fair to say that the brighter the better for us, because to a degree we don't really necessarily have so much. Well, there are some limits, of course, also in brightness in the positive, but it's more on the pointing and on faint targets. And clearly, when you start to go into M dwarfs, that's where you need to be careful in pointing. And so probably for the pointing around the magnitude 15 or something like that in the visible, it's somewhere where you need to be a bit careful of. But it's more the pointing than the actual measurements through detectors.
Well, but there's plenty of planets down to 15 magnitude.
Yes, and actually one would hope to stay actually much brighter than that. It's really, if you need to push, in particular for N dwarfs, so that's our very interesting targets. Yeah.
Okay. Any more questions here?
So I have two questions. First, for how many years the onboard resources would be sufficient to do the survey? Like how long you can extend the mission? So this is the first question. And the second question, am I right that this interesting angled design of the telescope is aimed to increase the area of the sky available while you keep the sun at the back?
Both excellent questions. I didn't have too much time, so I made a selection of graphs to show. But the answer to your first question is reassuring. We don't have any cryogen that is finishing, and so 6 years I'm hearing is very easy, but presumably even more than that. So I suspect that unless something goes wrong, what will finish will be the money at a certain point. That is so the money of the operations. But there is nothing from a technical perspective in principle that should prevent the mission to continue much longer. So that is reassuring. And then being L2 is great, you're right, because you can monitor very efficiently and effectively many planets in different areas of the sky. We have 100% visibility for planets close to the galactic pole, and this visibility goes down to 40% at any instant towards the ecliptic. But throughout the year, you can look at all the sky. And of course, you need to move your telescope inside a certain angle, because you really don't want to fry your detectors in the infrared, and so you need to make sure that basically the spacecraft is never really looking at the sunlight, and so you need to stay and do observation within this certain angle. Sorry.
Thank you very much for great and very interesting talk. You just mentioned that only one moon is a candidate. You think that maybe it's not candidate for the moon yet. But I wonder what is the main problem with detecting moons if you have so many planets, and when could we have sufficient progress to have them more and more and more? So what do you think? What is the time scale?
Thanks so much for your questions. Again, there is an entire literature by a number of teams around the world that were suggestive that, in principle, Kepler could already help to look at exomoons because the kind of exquisite precision you could get out of Kepler was good enough to look at this transit time variation and transit duration variation. But one of the issues that Kepler had was the cadence of the observations that was not necessarily good enough to see some of the signals. Of course, these are very small signals, and so of course you need to have high precision. This candidate moon was proposed, I think, was a couple of years ago or so by the team of David Kiplin in Columbia. It has been a bit controversial, and I guess one needs to have more observations. It's an interesting system if this confirmed, because the moon per se is as big as Neptune, and so you start to wonder whether it's a binary planetary system rather than a planet and the moon. But still, we know very little about this object. Yes, because the data are difficult to analyze, and ideally one would like to see even more data confirming or not that there is this object. Now, with Ariel, we could help with this question, in particular because of the infrared. The infrared has the advantage that you don't have limb darkening effects. You're less prone to stellar activity, contamination. And on top of that, we will have relatively high cadence in the observations. So we have a working group that is looking into that, and they seems to be quite pleased with the potential performance that the mission can do in contribution to this. Where Ariel was...
How long should we wait?
Well, Ariel is 2029, but maybe people will be able to do things before. I mean, of course, James Webb could also do that. The question is whether you can convince a TAC panel to use many observation of James Webb to look for exomoon. I think that is perhaps the challenge. So what I'm trying to say is that it is challenging, because if we weren't challenged, we would have already seen many other moons. And whether or not going in the infrared might help, for the reason I explained, we will see. But yes, it's an interesting topic, yes.
Okay, I see we have some questions on Zoom. Ewa Szuszkiewicz, please.
Okay, great. Thanks a lot, Giovanna. I enjoy your talk as always, Charles. And I would like just to ask a quite general question, which I'm interested in habitability, and what are the most pressing questions which you can suggest to theoretical studies in order to help Ariel to see more and to provide more output in the future? What will be the most pressing or few themes which you think that they must be the most important at the moment?
So Eva, thanks so much for your question. You're referring more to habitability or more in general, or in terms of models of these atmospheres?
Well, I mean, really both, because I think that they are linked together. We are trying to make a link between observation, interpretations, and theory, because they must go together. But I mean, Ariel, it will be a wonderful tool, and to use it to the most extreme, I mean, we probably can help if we are guided by the people who knows what will be the best thing for Ariel to see, or what it can be achieved.
Thanks so much, Eva. That's a great question. I think there are many areas where the theory really need to catch up. I think we all start to realize that the kind of tools that we're currently using to interpret current instrumentations will not be good enough for James Webb or Ariel. The data will be much superior to what we see right now, which is great, but it means that simplification, like what we are using now in the retrievals, which are good for the kind of data we're using, but not good for future data, like, chemistry that is constant with the pressure in the atmosphere, or simplification of 1D models. All these kind of things would probably not be good enough for data, to interpret data with James Webb and Ariel. And so there is actually already quite a lot of effort in the community to expand to the 3D models, both the circulation, but also the chemistry, the cloud formation. And clearly this is a huge and a big effort. When it comes to small planets in particular, I think we need also a lot of lab measurements for the interior to understand the equational states of some exotic components that may be on the interior. We don't know these equational states, and so extrapolating those at temperature and pressure that are very high it's clearly incorrect, and so we need to have more lab measurements in that, and even more understanding of what kind of chemistry you can have as a result of the contamination of the atmosphere from the rocks and components in the interior. Again, this is something that has started already, but clearly there is really a lot of work that needs to be done. Also, line list spectroscopy, it is also something that needs to be upgraded. I think groups like ExoMol, that there are UCL, but also other teams around the world have committed quite a lot of effort to go to line list at high temperature, and that was absolutely fundamental to look at the atmosphere or the ubiquitous. But now, to a degree, we need to do the inverse process. So we need to go to colder objects to look at the super Earths, but with compositions that are not necessarily the one that we're used to in the solar system. And from a spectroscopic perspective, it might change quite a lot. So as an example, we have just published a couple of papers looking at how the water is broadening when you have atmosphere that are really water-based, and also the kind of effect due to the water continue at low temperature when you have, again, this water-rich atmosphere. The effect is big and is observable, and this is just one molecule. You need to do that for several molecules, and so on and so forth. So we really need to upgrade all these models, and so the list is very long, and not even touching the study of astrobiology and life, because that is a very much longer discussion.
Thank you so much.
Okay, I'm afraid for the sake of time, I will have to stop this very inspiring and excellent discussion. So thank you very much. You left us with a lot of inspirations and questions still to be asked. So if people here are willing to continue discussing with Giovanna, she's around, right?
Absolutely.
And we'll be definitely in touch. So thank you very much. Thank you for the seminar. So let's thank our speaker again.
Thank you so much.
Thank you. And that's